So now that we have explained all the different types of atmospheres that we might have, let's assume a typical spring desert day, just around the desert here in Al Ain, for example, where it's dry enough that moisture plays no role. There are no clouds, and winds are light or moderate. At night, the ground surface has been cooling. Ground is a perfect black body radiator for infrared wavelengths, so meaning that it's efficient at radiating heat to the outer space. So ground surface is also cooling the layer of air above it. So if this is my ground, get the pen. If this is my ground, and now it's cool here on the ground. So basically, if this is elevation and this is the temperature, so here we'll have temperature will be going up like this. So the cooler part will be the one next to the surface, because the surface has been cooling all night. The cooled air layer nearest to the ground cools the layer of air above it, so we get steady flow of heat downwards from the air to the ground by conducting slight convection. So at dawn, temperature increases with elevation up to perhaps 1,000 foot. So if we look at it, it will actually go this way. So it starts with low temperature and it keeps going up as we go up. The cooling wave from the ground runs into the lapse rate left over from the previous day, and the temperature continues along up with the standard atmospheric curve. So here is the orange one is what happens at the dawn. So because the ground itself has been cooled, it keeps cooling upwards. So the temperature, there is an artificial increase when we go up, not the other way around, because usually it would have been going this way. Theoretically, it would have been going this way. So now remember what is this called when the temperature increases with elevation? This is what we call the very stable atmosphere, which we also call as an inversion. So below 1,000 feet, the temperature increases with height, forming an inversion. Inversions occur every clear night with low or average winds across most of land surfaces. Inside the inversion, extremely stable vertical disturbances are strongly dampened, meaning that whatever, if you are smoking in an inversion, the smoke will be right next to you. Imagine the inversion as a pot that has a closed lid. Above the inversion, mildly stable with standard lapse rate, disturbances are dampened, but less so. Now let's look again. What happens at sunrise? The ground heats up, warming the air layers above through conductions, convection, and radiation. So now after sunrise, we start to have increase in the temperature here. By 2 hours after dawn, the ground temperature reaches around 70 Fahrenheit. 70 Fahrenheit is, let's say, 18, 20 Celsius. The warmed air near the ground has an adiabatic lapse rate. So now we start going to the adiabatic lapse rate, which is this part over here. Let me use a different color, which will be the green color over here. So that will be the adiabatic lapse rate. Now, as the heat layer rises, it mixes with the remaining inversion, weakening the inversion. By mid-afternoon, the inversion is gone, with the warmed air extending up to 6,000 feet. So mid-afternoon, it keeps going at weakening the inversion, you see here. And by mid-afternoon, we are already almost here. By sunset, the ground cools, forming a weak inversion that grows overnight, repeating the cycle for the next day. And keeps going and going and going. Another factor that also affects temperatures is the mixing height. The mixing height is a key concept in air pollution meteorology. It represents the height to which vertical mixing occurs. Now, the mixing does not happen all over the atmosphere. It just happens in a very small distance above ground. In the mid-afternoon, vertical mixing occurs vigorously up to 6,000 feet with negligible mixing above. Let's look again. Mid-afternoon, you see mixing happens all the way till here. This is all mixing height. However, this is not the same when we're talking about dawn or when we're talking about 2 hours or 4 hours after dawn. The vertical mixing creates large-scale turbulence that also supports horizontal mixing, distributing pollutants uniformly up to the mixing height. The mixing height serves as the upper limit for the dispersion of pollutants. Imagine, again, you put a lid for your pot where you are doing your pasta. If you have a short pot, the lid will be close to the stove, but if you have a longer pot, the lid will be far away from the stove. This is what mixing height stands for. Morning mixing heights are much lower, but grow throughout the day, and they are higher in the summer than in the winter. Cloud formation is a visual indicator of the mixing height. So where is the cloud? The cloud is closer to the surface or it's far away. As small clouds often have tops at roughly the same height. At the troposphere-stratosphere boundary, air is very stable and resistant to mixing. Commercial airplanes often fly above this boundary. So because the sky is clear and contrasting with brown or gray skies below. So we can see here that clouds have irregular tops and sides, but flat bottoms. And this flat bottoms, that's the cloud tops are all at the same elevation, and this is now our mixing height. Also, another factor that affects the temperature is the moisture, as we have discussed earlier. If you just look at any ocean just next to the land and where it reaches the land, you will find that there is evaporation from oceans. This is, let's say, around 448 times 10 to the power 3 kilometer cube every year. Out of them, 411, they will be rained back on the ocean, and 102 will fall as rain and snow on land. Additionally, there is 65 that evaporate from the land, and there is 37 that go back from the ocean. So this cycle, it complicates the atmospheric behavior completely, because remember, we talked about how the moisture absorbs the infrared and it changes the lapse rate significantly. So most atmospheric moisture evaporates from tropical oceans. The residence time of water molecule in the atmosphere is about 9 days. So the molecule goes up, it stays 9 days, and then it goes back down. Also, moist air rise and the relative humidity increase due to decreasing pressure and temperature. And then moisture begins to condense when relative humidity reaches 100%. That's what the clouds, typically around 2,150 elevation. So if you look here at this graph between elevation on the x-axis and T over T node absolute or P over P node or relative humidity over relative humidity, we can see that relative humidity is increasing as we are increasing the elevation. This is the relative humidity in green. Let's look at the different color, the red. We will be looking at the pressure, which will be reducing as the elevation increases. And the blue one will be your temperature, which is also decreasing, but on a very smaller scale. So changes with elevation of temperature, total pressure, and vapor pressure of pure water with relative humidity. Cloud formation and rain shadow effects. The clouds form when moist air ascends from over mountains. And as air descends, it becomes drier, leading to cloud evaporation. This process creates rain shadows on the lee side of mountains, leading to dry areas like deserts. So if you really want to see a very good example of that, that would be if you drive to Salalah in Oman. You are driving, and I've done that myself. You go up in a mountain in the desert, and suddenly you arrive the top of the mountain, and here it's all desert. Once you come here, you are basically in fog, and here you have green, 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 green. And it's just a matter of a line that really divides the desert and the green areas. Most adiabatic lapse rate is slower than the dry adiabatic lapse rate due to the heat released by condensation, as we just talked about. In moist air, rising air can lead to thunderstorms if it continues to rise and condense. Evaporation of rain from thunderstorms into dry air can cause downdrafts and wind shear, hazardous to aircraft during takeoff and landing. Next videos will be talking about the wind and its impact on meteorology.